So today what we're going to be talking about is implicit differentiation. Now, so as of now, what I wanted you to do is for you to find df over dx, which would have been for this expression and for this expression. Now, before we begin, I guess I'll give you a little bit of time for you to work on this question. How about that? So f of x is equal to x times another expression called g of x. In that case, what is df over dx? Now, the second question would have been this. We have x times f of x is equal to x squared. In this case, how would you find the f over dx? And we'll see what we end up getting. All right, given that you spent some time working on these, if you didn't, you can pause this video a little bit and then you can continue once you are done. Now, so for the first question, we have is df is equal to x times g of x. Now, since we have two functions, or two expressions rather, it's multiplying, one being dx, the other one being g of x, we could use the product rule to get the answers here. Now then we have df over dx would have been equal to x times the derivative of g, which means dg over dx, plus derivative of x, which is simply 1 times g of x. Alright, so in fact our final answer becomes, just like any other product rule, we have x times dg dx plus g of x. Alright, that becomes our final answer. How about for the second case? Oh, okay. I guess I can see that some of you guys might have done this question a little bit differently. So first, I guess first option would have been something like this, I guess. Since we see the x on both cases, we can divide by x, given that x is not equal to 0. Now, then we will end up getting f of x will simply be equal to x, given that x is not equal to 0. Alright, that's the first method. Then, in this case, we will end up getting the answer rather quickly. Here we get to see df over dx will now becomes 1, using the power rule. Okay, now, but what if we are to do this one a little bit differently, using the second strategy? Second strategy will be, instead of solving for f of x, what if we just use the product rule? Because just like earlier question, we'll see we see the product between x and f of x. So what if you use the product rule to get the answer? And we'll hopefully we'll see if this will get us the same answer as before. Oh no. Okay, so first we'll be using the product rule here. We will have x times df over dx plus f of x. Now that's equal to 2x. We can take the derivative of the second part. Now then, what we want to do is, hey, wait a minute, f of x is equal to x. Earlier, we were able, for this question, we were able to figure it out. So what we like to do is we can just continue on with that. Then we will have df over dx. In place of f of x, we will have x by itself, which is equal to 2x. Then, of course, we can subtract x on both sides. We'll end up getting x df over dx will be equal to x. And then when you divide by x, then we will realize that df over dx is equal to 1. Haha, wait a minute. Whether we isolated the f of x by itself, or we didn't, one way or the other, we will end up getting the exactly same answer. That's quite interesting, because what if we have other questions in that similar circumstances, where what if we cannot, solve for that particular variable? Can we still find the derivative? Just like the example that follows right here. So we have x y squared plus x squared y equals 7. Now, I want you to find y prime. Let's look at number 3 for a second. Before we continue, I want you to look at that expression. Alright, now, then when you look into that expression, can you easily isolate y by itself? In fact, it is more than possible, definitely, but we're gonna assume that it'll be quite difficult. In fact, when you isolate y by itself, it will be somewhat ugly but familiar looking expression. I'll make a comment on that later. Here, what if we assume that we cannot, or just, it is quite difficult for us to solve for y, then can we still find y prime? Let's try to do this one by this way. You see, y, in fact, those of you who feels more comfortable with y being f of x, then what we can do here would have been, we can assume that x times f of x square plus x square times f of x equals to 7. All right. When we first, of course, we have to use the product rule here on the left side, and so is the right side of that left portion of the equation here. Here we will end up getting x times derivative of that, which is 2 times f of x, multiplied by the derivative of the inside, which is by chain rule, we're going to have f prime of x, which is basically df over dx. Now, on the right, and the second portion becomes plus f of x whole thing squared multiplied by derivative of x, which will be equal to 1. So we can just leave this one in this way. So this portion is a derivative of the first term. Now, second term will be plus. We have x squared times the derivative of f, which becomes simply f prime of x. Now I'm going to just go to the bottom here. Plus f of x times the derivative of x squared, which is simply 2x, is equal to 0, of course. Now here we have, this will be the derivative of the second term, and then the other side, derivative of 7 becomes 0. Now, then, if you were to organize this one just a little bit, what will we end up getting? In place of f of x, we're going to plug in y, and in place of f prime of x, we're going to plug in y prime. Now, one of the reasons why I have done it this way is because for some of us, trying to see the chain rule out of y squared is somewhat difficult. On the other hand, if you see y squared from, if you have to see chain rule from f of x, entire thing squared, it's somewhat easier for us to see. That's why I changed it to f of x in place of y. But you could have used the y by itself from the beginning. That's what we like to do from the second one and on. Here, then if you have to rewrite this one, we'll end up getting 2xy times y prime. For the first one, I just rewrote it, plus y squared. Now, on the other side, we have plus x squared y prime plus 2xy is equal to 0. Now, then since we are looking for y prime, we can move all the other things except y prime on the left side. We have y prime, then we can factor out 2xy plus x squared. Now the other side will be equal to negative 2xy, and when we subtract 2xy from each side, and then how about y squared? Will be also negative y squared. Now, then of course, y prime then is equal to, we just have to divide this one by the other one. So we have negative 2xy minus y squared all over positive 2xy plus x squared. Now that becomes our final answer. Now we'd like to go for number 4, x equals sine of xy. Now once again, in this case, what we like to do is we could assume that y is equal to f of x, but we're just going to keep it like that. Now, here it goes. Then derivative of x becomes simply 1. Derivative of sine of xy, we can definitely use the chain rule with the sine, and then product rule. Chain rule with the sine, and then first layer being the sine, and second layer being xy, and then we can use the product rule for xy to continue on. Therefore, let's try to look into this one. Sine is equal, derivative of sine is cosine of x, or cosine of xy. And then by the chain rule, we have to multiply by the derivative of inside, which will be x times, yes, derivative of y becomes y prime. Here, you see, we are assuming, get it? Assuming, meaning we are implying. In this case, we are using the word implicit, as we talked about it way in the beginning, implicit. We are implicitly assuming that, implicitly implying that y is function of f of x. Now, then we will realize that the derivative of y is becoming simply y prime instead of 1 plus y by itself, because derivative of x is 1. Then here we will have 1 over cosine of xy is equal to xy prime plus y. Now, of course, we can subtract y from both sides, and then in fact 1 over cosine becomes secant, so we can even write it as a secant xy minus y is equal to xy prime. Now, finally, what we can do is to have y prime by itself, we can divide by floating by x. Therefore, we have secant xy minus y entire thing divided by x equals y prime. Alright, so that is our answer. Then for the next 2 more questions, we'll like to look into a bit more complicated stuff. Here it goes. We have y in 2 places, here and here. Notice, since we are not solving this one for y by itself, what we can do is we are implying, implicitly we are taking the differentiation, assuming that y is the function of f of x. Then left portion is basically the same as before, as in by the product rule, we will have y squared times derivative of x, which is equal to 1, plus x times the derivative of y squared, which is 2y, but since the function y is the function of x, we gotta use the chain rule to multiply by y prime. Now that's the left side. How about the right side? Because this portion, if you have to rewrite it, it will be secant of y entire thing to the 1/2 power. So first we will have 1/2 power, and we will have secant y the negative 1/2 power, and derivative of inside, meaning the derivative of secant, is secant y tangent y, and then multiply by the derivative of inside, innermost side, which will be y prime. Now you see that we see y prime here, y prime over here. So if you have to rewrite this one, for example, we will end up getting something like this: y squared plus 2xy y prime, which is equal to, now when you combine this one and this one, you will realize that 2 will be in the denominator, and we will have square root of secant of y times tangent of y times y prime. Now, then, since we see y prime in two locations, we will have y squared will be equal to square root of secant y times tangent y over 2. And then as we are bringing this term over to the other side through subtraction of 2xy y prime, and we're going to factorize y prime, then we will have minus 2x y entire thing by y prime. Now, then what we end up getting here would have been y prime will be equal to y squared, and then secant y times tangent y over 2 minus 2xy. So this becomes our final answer. Alright, how about number 6? After number 6, we're going to try to go back to number 3, and I will just set up another solution. Not that I'm going to finish it, but I'm going to set it up, and then so that you can kind of be able to see that also. Let's look at number 6 together. Here we have left side is rather simple because we can just write it as 12 x to the third power by the power rule. But on the other side, we have to use the quotient rule here. So, well, first denominator square, y squared minus 1, entire thing square. And then here we will have y squared minus 1 times the derivative of the top, which ends up being another product rule here. So we have x y prime plus y minus, we have xy times the derivative of the denominator, which would be 2y y prime. Now notice, if you have to simplify this one, you will see two locations where we have y prime. One is right over here. The other one will be, right over here. Those are the only two locations. So therefore, why don't we multiply both sides by y squared minus 1, and then continue further from there. So we will have 12 x cubed times y squared minus 1 square, and here the first term becomes x y squared by multiplying this term to this one, or maybe I try to put them together, or maybe I just leave it in that way. And then y prime minus xy prime and plus y cubed and minus y. Now, on the other side we have minus 2x y squared y prime. Notice that xy squared is common here with the y prime. Therefore, if you have to bring everything onto the other side that are not part of the y prime, you will end up getting something like this. 12 x cubed y squared minus 1 square minus of course, these two terms will go over to the other side, but why don't I factor at the same time? If I were to factor out negative plus y, then we will have y squared minus 1. But in fact, sorry about that, we should have that to be negative. Now, on the right side, since these two will cancel out, what we'll end up having here is negative 2x y squared actually will be combined with this term, so we're going to have negative xy squared y prime, and then we will have negative xy prime. Now, another thing that which we get to realize is that xy prime is common in both terms, and you will realize that we can factor out y prime by itself, then we will end up getting negative x times y squared plus 1, you see in this case they have the same sign, times y prime. Now, if you have to combine the left side, what we'll end up getting is this. Since y squared minus 1 is common in both cases, y squared minus 1 times, here we have 12 x cubed will be multiplying to y squared, which becomes this way, and minus 1, then minus simply 12 x cubed. Now, and then on the other side we will have only y by itself. Then in conclusion, what we end up getting is y prime here will end up being y minus y squared minus 1 times 12 x cubed. I'm just copying down this portion first, minus 12 x cubed minus y, but divide the entire thing by this expression, which is negative x times y squared plus 1. Alright, that's it. Now, so when you go back to number 3, how else were you able to do this one? In fact, my hint would have been this. If you had to solve for y, then what we could have done is this: x y squared plus x squared y minus 7 equal to 0. Now then you will realize that this is a quadratic equation in terms of y. So therefore you will realize that this is equal to a in quadratic formula, this is equal to b, and this will be equal to c. So therefore y could have been solved as negative x squared plus or minus square root of x to the 4th minus 4a, a becomes x, c becomes negative 7. The entire thing divided by 2x. So this one was actually possible in this way, and then when you take the derivative, you should be able to get something that is equivalent to this one. Alright, that's it for now. We talked about implicit differentiations, and have a nice day. Bye-bye.